Hello everyone. In this video, we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular, we will begin to discuss matter waves. Alright, so given our analysis of the photoelectric effect, we've seen that light and radiation exhibits properties of both waves and particles. Okay, the wave properties we've seen were all in topic 9, so interference, diffraction, polarization, etc., etc. And the particle property is what we've talked about for basically the last subsection. That is the photoelectric effect, which in its classical formation really contradicts what we had understood about light and radiation as a pure electromagnetic wave. There is still sort of a little aspect of waviness in here, in that the energy is proportional to the frequency. But big picture, the visual of these little wave packets is much closer to the property of a localized contained particle with a discrete amount of energy. That's the essence of the photoelectric effect, and it is in contradiction with the assumptions underlying our analysis of interference, diffraction, and polarization. This is not a small claim here. Light and radiation are, in different circumstances, exhibiting contradictory properties of both waves and particles. And so that raised the question at the time, does matter as well exhibit properties of both waves and particles? It's worth noting this is not an obvious follow-up question, but it was in fact followed up on, and as it turns out, it's going to be quite relevant here, because the answer is yes. But if the answer is yes, then question, what would the wavelength of a matter particle be? Right? What would the wavelength of a matter wave be, I guess? And then what would the wave be in? Okay, these are like, if we're talking about particles having waviness, what is the wavelength and what is the wave in? These are very good questions, but we're going to begin this here, and the answer to these questions is really sort of, together with the photoelectric effect, the foundation of the quantum revolution. So we're really going to reconceptualize basically all of what we understand about fundamental physics here. So jumping in a little bit, in 1924, Louis de Broglie, this is how it's said, Louis de Broglie is a Dutch person, proposed that the wavelength of a physical particle would be related to its momentum, all right? And in particular, he established the de Broglie hypothesis, which is that the wavelength of a particle would be equal to h, Planck's constant, divided by its momentum. And this was a hypothesis at the time, but it did not come out of nowhere. It is worth noting this was a radical idea at the time. It's still relatively radical. And as it turns out, it comes from special relativity. So a brief digression. As you might remember in special relativity, one of the equations derived is the relationship between energy, the rest mass, and the momentum. And this is the real version of an equation many of you have memorized in popular science, which is that E equals mc squared. As a quick reminder, this relates the energy of a particle to its rest mass and its momentum. If a particle is not moving, the momentum is 0, and that gives this bit, which just says E equals m naught c squared. So for a non-moving particle, the energy is equal to the rest mass times c squared. But de Broglie went in sort of an interesting different direction. He said, well, look at this. For light, if I, let's say I needed to associate the wavelength with a momentum. Well, I can use this relationship here to sort of take a guess. For light, the rest mass of a particle is 0. Okay, the rest mass is 0. So what if E is equal to P times C for light? This relates the energy to the momentum, and this is all we needed. Because if the momentum is equal to the energy divided by the wavelength of light, And the energy is equal to h times the frequency, which is equal to hc divided by the wavelength. Then the momentum is equal to E over c, which is equal to hc over c times lambda. And therefore the momentum is equal to h over lambda. So that relates the wavelength of a wave to its momentum. Now notice, this derivation, quote unquote, is for light in particular. And so the de Broglie hypothesis basically says, well, if there was going to be a wavelength for a matter particle, maybe it would look like this. Maybe it would be related to the momentum of that particle. And as it turns out, experimental evidence for matter waves followed quickly through what is known as Davis and Germo's electron diffraction experiment, and that will be the subject of the upcoming videos. One final thing, actually, before I move on, take a look at this equation. You might ask yourself, we deal with many, many, many macroscopic objects with sort of human-sized momenta. So if a person is sort of walking along at 2 meters per second and they have a mass of approximately 100 kilograms, then their momentum is going to be approximately 200 kilogram meters per second. But notice that that means their wavelength will be on the order of h divided by that number. H is already 10 to the negative 34 or so, and therefore their wavelength would be on the order of 10 to the negative 37. So the reason we don't see the wave nature of ordinary macroscopic objects is the wavelength predicted by the de Broglie hypothesis is simply too small. And in fact, you need a tiny, tiny, tiny momentum in order to get any kind of wavelength behavior. And so we need objects for which you can have a tiny momentum. And even then, we're talking such a small wavelength that the objects themselves need to be very tiny. And so the objects that first exhibited this behavior, where we first showed this behavior, were electrons. And we'll get to that in the next couple of videos.